Welcome to the lecture series on condensed matter physics. This field condensed matter physics is an interdisciplinary, cross-disciplinary and multidisciplinary field. The subject condensed matter physics does not mean, because the word physics is there, it does not mean it belongs to physics alone. As the slide will show, this physics, this area connects several fields. You see the condensed matter physics here, but it connects biophysics or medical research, maybe Covishield. It does not mean that the solid state physics alone, and the other materials in the liquid phase also it is covered by this field. Now, this is a book on solid state physics, but of course, condensed matter physics generally refers to solid state materials, and this field would not have become popular, but for the fact that in 1960 the invention of transistors made it this condensed matter physics as a very important field. Without this nobody can lead a comfortable life today. I am able to see you. I see we have the computer, we have the calculators and supercomputers and so many other things, and the communication has become one of the very important things. Foster communication. What do you mean communication? The current. What is current? Current is nothing but the flow of electrons. Therefore, condensed matter physics deals with how electrons, not only electrons, other ions, phonons, magnons, several other ions are responsible for explaining the advanced materials. I have got here at the left hand top. Advanced materials means aerospace materials and rockets and so on. At the bottom I have got biophysics, as I told you. On the other side we have quantum computation. In about 10 years time, the computers that we are using today will become obsolete, will become useless, they will be thrown out, they will be replaced by quantum computers. So, quantum mechanics plays a very important role, and you find here nanoscience and technology, nanotechnology. When you have got a fewer number of atoms, you talk of nanotechnology, right. Therefore, the strongly correlated systems which tries to explain the phenomenon of superconductivity, which till date remains unexplained. It is one of the unsolved problems in solid state physics till this year 2023, right. Therefore, condensed matter physics is a very broad field connecting various areas. So, as I told you just now, electrons are responsible for electrical conductivity. So, how free electrons are obtained in solids consists of formation of free electrons, classical free electron theory of metals, and the experimental demonstration for free electrons. Experimental demonstration implies whether free electrons which was proposed by Drude and Lorentz, whether really in metals or really in solids, whether do they exist. That is a fantastic experiment, is shown by Tolman and Stewart, that free electrons do exist in solids. So, even though the free electrons are there, to start with, the free electrons are treated on the basis of classical free electron theory. To start with, I will deal with the classical free electron theory, then I will go back to particle in a box, density of states, free electron parabola, Fermi-Dirac distribution function. These things are important when you deal with them, especially semiconductors. The semiconductor is important because of the transistors, right. The transistor is one that is used in the communication, your computer, everything, the transistors. Now, the classical free electron theory is the existence, the respect that we have to give, it is due to you have the Drude and Lorentz theory. This is the classical free electron theory. The quantum free electron theory was given by Sommerfeld. The quantum free electron theory means you make use of quantum mechanics. On the other hand, classical free electron theory due to Drude and Lorentz, they thought at that time there was no quantum mechanics. So, initially they treated the electrons as if they are just gas molecules, because the gas laws were known. Therefore, let me talk of sodium atom. Sodium atom will become a sodium ion when the outermost electron is stripped. You see, this atom loses the outer electron, and then you have sodium ion, right. When the outermost electron is removed, sodium atom becomes a sodium ion. Where does the electron go? It goes to the metal, it goes to a solid, right. If you take sodium solid, if you have got 100 sodium atoms to start with, you combine 100 sodium atoms. Sodium has got valency 1, that means the electron number, the number of electrons in each sodium atom is 11. The 11th electron is a valence electron, right. Valence, if you bring 100 sodium atoms, what will happen to valence electrons? All the valence electrons, there are 100 atoms, means there will be 100 valence electrons. The outermost electron is called a valence electron, right. All the 100 valence electrons will become free. Valence electrons become free electrons in solid. Because they become free, they can take part in electrical conduction and thermal conduction, right. So, the electrical conduction in a metal or a semiconductor is due to the electrons. Similarly, thermal conduction also is due to the electrons. Now, therefore, this is a very important sentence. Valence electrons of atoms become the free electrons, and these free electrons are the conduction electrons when solids are formed. And so, in solids, the valence electrons become free electrons when the solid is formed, and they become the so called conduction electrons, and they are responsible for the electrical and thermal conductivity. I will go back to sodium metal again. I have the sodium metal here. For this atom, which was earlier the atom, but the electron from this atom has come out, right. Similarly, the valence electron become free electrons. So, you have the delocalized or free electrons, and when the electron is got rid of from its parent atom, it becomes a ion, it is a positive ion, right. So, how do you visualize a sodium metal? Sodium metal consists of sodium ions and free electrons, is that right? Sodium ions and free electrons, and these free electrons, which are shown by red dots, are responsible for the electrical conductivity. If you put two metal plates and one connected to a battery here, the other connected the negative of the battery, there will be a current. The electrons will go towards the positive end of the battery, positive side. This is the positive, this is the negative, means electrons will go from here to there, the positive end, right. Now, therefore, that leads to the electrical conductivity, the metallic bonding. That is how you explain the metallic bonding, and the free electrons float in the solid, right. So, it is called a free electron gas. You see the electrons, they float in the positive ions form the background, right. The positive ions form the background. This is called the free electron gas, right. This free electron gas, at the time of Drude and Lorentz, they were unaware of quantum mechanics. There was no quantum mechanics, right. So, they treated these electrons similar to the gas molecules, which was proposed by many people to deal with the gas laws, the Boyle's law, Charles' law, and so many other laws, right. So, the electrons are treated like gas. That is the reason it is called a free electron gas. Electrons not classical objects like gas molecules, but however, at that time they treated the electrons similar to gas molecules. And what do the molecules do in a gas? The molecules will be floating here and there. If you take a gas, if you take this room, you have got air molecules moving around me. The air molecules will be moving and hitting. If the fan is on, the molecules will move with a faster velocity, and they will go and hit. The molecules cannot be seen by eye, right. So, the molecules will go and hit the other molecules, and they move in random direction. The molecules will be moving in a random direction. So, Lorentz treated the free electrons to be similar to the molecules in a gas. The gas molecules randomly move and collide with each other, right. Similarly, the free electrons, according to Drude and Lorentz, similarly the free electrons are randomly moving in the metal and collide with the ions, right. However, at the application of electric field, they experience a drift towards the positive end. First, let me tell you, when you do not apply any field, the electrons will move randomly and collide with the ions. Okay. Secondly, when you apply a electric field, they will experience a drift, because the electric, what is the function of the electric field? There is a positive polarity, the electrons will have a tendency to move towards the positive polarity, it will give us a current. So, therefore, over and above the random distribution, randomly moving electrons, there will be a compulsion for the electrons to move towards the positive end, because of the external field applied. So, they experience what is called a drift, or we will talk about the drift velocity. The random velocity, random motion is there, over and above that there will be a drift velocity. Now, the question should be asked by a younger student, you talk of free electrons. Do you have free electrons in solids, in metals, right? We talk of electrons and holes in semiconductors. One asks the basic question whether free electrons do exist in solids. It was Tolman in 1917 who showed by a simple experiment, Tolman and Stewart. They demonstrated that is the first direct experimental evidence for the existence of free electrons in metals. A fantastic experiment. Now, in which what they did is you take a long tube and have some pebbles or rice particles, right, in a long tube, and give a sudden jerk. When you give a sudden jerk, the particles will move in a opposite direction. If it is given a jerk in the left hand side, all the particles which are sand particles or rice in a glass tube, they will be thrown in the opposite direction. So, because the electrons are thrown in the opposite direction in a metal, if a metal is given a sudden jerk, it was found when a piece of metal is accelerated sharply, then the free electrons by that inertia will be thrown towards its rear, the other end, leading to a detectable pulse of current. Now, this particular experiment has been discussed in the book written by Cottrell, Introduction to Metallurgy, Physical Metallurgy, and only the other book which deals with this is the one that I have written on solid state physics in the year 2015. Now, these are the two sources available which talk about the Tolman and Stewart experiment, the ingenious experiment which shows the existence of free electrons, right. They are very important experiment, right. Now, there are umpteen number of methods by which we can study the free electrons, right. So, in order to explain the electrical conductivity in metals, Lawrence and Drude put forward a theory called the free electron theory of metals. It is based on the following assumptions. This I have told you already, the free electrons in metal resemble that of the molecules in a gas. The kinetic theory of gases can be applied to the free electrons also. You talk of average velocity, then you talk about the average kinetic energy, then they are moving in random directions. When they are moving in random directions, obviously the current will be, electric current will be 0. Okay. When you apply an electric field like this, you have got a positive here and negative here, then the electrons will move in this direction towards the positive polarity, right. Now, what will be the current? The current will be number of electrons in this volume element, right. In this volume element, we can have V here and or Vx here along the x direction Vx, and n is the number of electrons per unit volume. So, in this volume Vx is the diameter can be taken as unity. So, Nvx is the volume and each electron will carry a charge E, therefore, the current will be N into E, that the volume, the number of electrons in this volume Nvx multiplied by E. Minus E is the, because the charge associated with the electron is minus E, therefore, the current along the x direction will be given by NeVx, right. So, I think according to Ohm's law, the current Ix will be sigma into Ex, Ex is the applied field, and the same current in terms of electrons will be given as Ix is equal to minus Ne into Vx, right. Obviously, Nvx is the volume. the number of electrons n Vx gives the number of electrons in the volume. Vx is the length and the diameter, as I told you, unity. So, n is the number of electrons per unit volume. Therefore, the current will become of this expression. Then you can combine these. Now, this I told you random motion of the electrons. The electrons will move when you do not apply any electric field, the electron will come and hit the ion, it will move in this direction, then it will move in this direction. So, you see the electron coming here, it will move and collide with the ion and go in this direction. But when you apply electric field, what happens is I think I should tell you about relaxation time. Relaxation time, from the instant of sudden disappearance of an electric field across the metal, you switch off the field. The average velocity of the conduction electrons decays exponentially to 0 because the current has been switched off. So, the electron has to come to rest almost, right, and the time required in this process from the average velocity to reduce to 1 by E times its value is known as the relaxation time. That is the definition of the relaxation time. The velocity Vx of the electron in terms of the relaxation time tau is given as Vx. Vx is what? Force minus E is the force which is being acted on the electron, F divided by m, right, force divided by m into tau, that gives the velocity, right. Vx is tau. If it looks Vx is from this expression, it looks as if Vx, the velocity will increase with time tau. That is not right, because it cannot be indefinitely increase with time. Therefore, there should be collision, right. So, drift velocity is defined as the average velocity with which the free electrons get drifted towards the positive end of the conductor and the influence of the external field. As I told you, there will be random motion. Apart from random motion, there will be what is called a drift velocity, because you apply an electric field, then the electrons should move in a particular direction, that is positive polarity. Therefore, there will be both the drift velocity and the random velocity, because of there will be collisions. The drift, because the applied field, the dVx by dt is the acceleration, right, the dVx by dt, that will be given by minus E, the force divided by m. A acceleration is nothing but E into Ex, that is the force divided by m, that is F is ma, right. So, this is the force divided by m is the acceleration. So, the acceleration that the electron receives by the field, and this is the acceleration that is due to the collision, right. Therefore, the two things put together will become 0 in a steady state. When no field is applied, the field, this will be this and this sum, the above two expressions will be equal to 0. Combining the above equations, you write the Vx, the drift velocity, as minus E tau by m into Ex, using the above in 2 and comparing with 1. The 2 and 1 are the two equations I had, right. If the electric field Ex is suddenly switched off, this I told you, Vx of t will be Vx of 0 into e to the power of minus t by tau. As time goes on, how the drift velocity goes back to the velocity of the electron when no field is applied, right. And this is what I told you, these two Vx will be E tau by m into Ex. Use the above 2 and comparing with 1, this is a very important expression. Ne square tau by m is the expression for the electrical conductivity, right. The electrical conductivity sigma will be equal to Ne square tau by m, and E tau by m is called the mobility. I will come to that later. The Ne square tau by m is the electrical conductivity. E tau by m is called the mobility, that will be made use of in semiconductor. This is how the electrons behave, as I told you, the the random motion, the hitting the ions, and when you apply a battery, the electrons have a tendency to move in a particular direction. The important thing is this expression is of greater importance, right. Sigma, the electrical conductivity, will be the number of electrons per unit volume multiplied by charge E, and mu is what? E tau by m, as I told you just now. Mu is the mobility. So, this expression is of very great importance which will be used or you would have studied in the area of semiconductor physics or semiconductor electronics. You have written by Z or Kittel or by me or any other book. You have them. The conductivity in a semiconductor will be partly due to electrons, partly due to the holes. But in the case of metals, you do not have holes in general. So, you write the electrical conductivity in terms of N, that is the number of electrons per unit volume, charge multiplied by mobility. This is the equation of central importance. It is the most important equation that one should have in mind. That will be extended to semiconductors, where you have the current due to the electrons as well as the holes, right. I will write N suffix E, then N suffix plus N suffix H, where N suffix E refers to the number of electrons, N suffix H refers to the number of holes, right. Then correspondingly I will write the mobility mu E, and the second expression will be mobility of hole mu H. That will be, so this extension of this to semiconductors will be, you would have studied elsewhere. I will also occasion to come to that later, but anyway this is a very important expression. The acceleration, as I told you, is given by the expression minus E, the force divided by m is the acceleration, that all of you know. And the classical free electron theory fails, because electrons are not classical particles, right. They are not like gas molecules. They have to obey the Pauli principle. You cannot have, if one asks the question, how many electrons you can have in lithium? You got 3 electrons. Can you put 1 as 3, the electronic configuration? You cannot have 3 electrons in the S state. There are rules which the Pauli principle, which says that only 2 electrons can be kept in a quantum state. Therefore, this classical free electron theory, it differs. It should be replaced by quantum free electron theory. To that pass on now. So, electrical and thermal conductivities could not be explained by classical free electron theory, right, because it treats the electrons as gas molecules totally wrong. At that time there is no classical quantum mechanics. Therefore, what was done by Drude and Lorentz is okay, but Sommerfeld came into the picture later. So, again it fails to account for the things like specific heat, the temperature dependence of electric conductivity, dependence of electric conductivity of electron on electron concentration, and then not only the specific heat, electrical conductivity and things like that. Many things cannot be explained by the classical free electron theory, because the fact that electrons cannot be treated like gas molecules. Therefore, you have to pass on to quantum free electron theory, which was proposed by largely by Sommerfeld, right. The energy values of conduction electrons are quantized. The energy values gas molecules are not quantized. They are classical particles, they can travel with all possible velocities. But on the other hand, even in the high school you would have studied 1s2, 2s2, 2p6 and so on, different electrons in the Bohr atom model. You would have studied the first orbit, second orbit and third orbit, and they will have discrete energies. Therefore, the discreteness or quantization, the energy values of electrons should be quantized. This quantization comes from by studying what is called the problem of a particle in a box. I will be talking about particle in a box. The allowed energy values are realized in terms of a set of energy values. The distribution of electrons in various allowed energy levels occur as per Pauli exclusion principle. I told you that the Pauli principle says that in the case of lithium atom, you have got 3 electrons, but you cannot write 1 as 3. You have to necessarily write 1 as 2, 2 as 1. The S state can occupy only 2 electrons, and the third electron has to necessarily go to the second shell or the second orbit. So, you write 1 as 2, 2 as 1. That is the Pauli principle. Therefore, the allowed energy values are quantized. Quantized the discrete energy values. If you take cricket ball, the cricket ball can move with all velocities, right. The player can run for 1 run or 2 runs, or you have them 4 or 6 and so on, sixers. But as far as electrons are concerned, they can have only discrete energy values. The electron can have only quantized or discrete energy levels. It cannot have continuous energy levels like classical objects like cricket ball, football and so on. they are the classical objects. The electrons, protons, neutrons, there is only discrete or quantized energy values. This quantization comes by studying the problem of particle in a box. We used to ask a question, what is meant by particle in a box, right? Particle in a box refers to a bound state problem. As given in Arthur Beiser, an electron bound to an atom or a molecule or a solid is the particle in a box. In a potential box, the particle can never escape from the potential box. The reason is the following: the potential goes to infinity at the end points, therefore, the wave function at the end points cannot be finite. The wave function should go to 0 at the end points. This is a particle in a box problem, which I will deal with in a greater detail in the next lecture. But the point is, to summarize, I should say that condensed matter physics is a highly interdisciplinary field. The invention of transistor made a revolution in our lifestyle. First and foremost thing is to understand how electrons behave in metals. So, the condensed matter physics means electrons, phonons and other ions, how they behave in metals, semiconductors, insulators. They are to be living beings or otherwise rocks or mineralogy and geology. Wherever you are, you should have the electrons, right. How to deal with the electrons is an essential thing that is there in the condensed matter physics. Free electron theory was proposed to obtain the electrical conductivity in metals, which is a failure. We will close this first lecture with this, and then we will go to the particle in a box problem in the next lecture. Thank you.